So today we will be discussing chaos as a concept, but also as a mathematical formulation, so as to better understand its consequences and its causal relationship with reality. The yin and the yang and chaos. Ancient Chinese thought recognized that chaos and order are related. In Chinese myth, the dragon represents the principle of order, yang, which emerges from chaos. In some Chinese creation stories, a ray of pure light, yin, emerges out of chaos and builds the sky. Yin and yang, the female and male principles, act to create the universe. But even after they have emerged from chaos, yin and yang still retain the qualities of chaos. Too much of either brings back chaos. So, herein lies the ontology of chaos, as presented by this logical mathematical book. I have to say that I bought this book in Kapuskasing, Ontario, in Canada. Was it Timmins? Timmins, and it was purely on the extravagance of being introduced chaos, right? For $9, it's quite a steal. And we start with a great start, with a nice pictorial image representing the sense of yin and yang and the dragon's enactment onto the yin and yang, which is the order, which is a spherical in that case, but ultimately which kind of brings a form of something to be understood in the totality of the chaos which surrounds you, right? And so in this case, the author, which is Ziauddin, Sardar, and Iwona, Abrams. And so, first page, there's this sense of ownership of value in the totality of existence, as it is hardly ascertainable, right? So, next page is ancient chaos. Hesiod, a Greek of the 8th century before Christ, wrote the Theogony, a cosmological poem which states that first of all chaos came to be, and then the earth and everything stable. The ancient Greeks seem to have accepted that chaos precedes order. In other words, that order comes from this order. Nothing further was made of this mythical idea until recently in the 20th century when chaos theory arrived. So they propulse themselves into the 20th century as we kind of reconvene with new forms of theory which are deemed acceptable, right? Or deemed worthy of consideration. That is to say that I think in between ancient Greece and the 20th century, we did explore the interrelationship between chaos and order. But I think this book is kind of referring specifically to the newly emerging perception of mathematical-logical application. And so when we talk about chaos theory, is a new exciting field of scientific inquiry, right? And so we are firmly situated in science. The phenomenon of chaos, and therefore the apperception of the phenomenon, is an astounding and controversial discovery that most respectable scientists would have dismissed as fantasy just a decade or so ago. But today it is seen as one of the most notable since the advent of quantum theory in the early 1900s. If chaos theory fulfills its potential, it will dramatically change the way we view the natural world and ourselves. And the example is the fractalized broccoli, which is a vegetable which demonstrate the fractalization of the growth, or what would essentially instantiate as a fiber growth of fractal patterning. Okay, so why is chaos exciting, right? Because now we're at a point where we're not only commanding the genome of plants to proliferate in certain ways, it also naturally occurs, right? So whoever is the intellect which brings us to do this is just a specific instantiation of intellect as it is, right? And so if one industry ends up capturing a certain scientific moment into a technologizable object of a commodifying potential, or and as such becomes a commodity which is profitable and marketable, then it is of the essence of our capacity to use our intellect to perceive reality in a certain way, which allows us to create such an object of value. And chaos theory is found precisely within this world of consequentialism and causal interrelationship. So chaos is exciting for all these reasons, right? It connects our everyday experience to the laws of nature by revealing the subtle relationships between simplicity and complexity, and between orderliness and randomness, right? Again, what would Hegel would characterize at the beginning of the Phenomenology of Spirit as simplexity, which is the state of the yin and the yang. It's the state of non-conclusivity which comes out of order and disorder. It presents a universe that is at once deterministic and obeys the fundamental physical laws, but is capable of disorder, complexity, and unpredictability, right? So the dissociation and further demarcation of what is determined and obeyable in terms of the fundamental physical laws, right? Whole sciences and academic institutions are built upon these principles, but also have been put into question by the fundamentally powerful, dynamic, and inquisitive force of disorder, complexity, and unpredictability. So it shows that predictability is a rare phenomenon operating only within the constraints that science has filtered out from the rich diversity of our complex world. So now we arrive at the necessity to filter what is in fact causally caused by your presence and what is caused by the interrelationship of your presence with all the contingencies of the external world which is found surrounding you, right? So it opens up the possibility of simplifying complicated phenomena. Precisely because so many variables can be accounted for, right? And only can be accounted for are contained within the context, right? And so depending on what you account for, you can have very, very precise results onto what you're trying to accomplish with varying degrees of response from the external world. So it combines imaginative mathematics with the awesome processing power of modern computers, right? So because at the end of the day, what we're discussing is the fundamental recalibration of a moment based upon the active potentiality of your being in that moment. It casts doubt on the traditional model building procedures of science, right? Because what we're proposing is constant rebuilding and emergence of model, right? And so it's the doubt is purely, and I would say that this is the book talking, not me. I think the doubt is based upon a form of healthy skepticism, but which must be integrated in the process. There is no way other than to be skeptical as well as furthermore integrative. That is the only way of repurposing yourself to the extent of effectivity. I think in a in a context of work, but in the context of teaching, then I think the doubt or the skepticism is much more allowed than in the context of pure actionability or operationality, right? Not necessarily in the formation of an opera, but do think about the intermediation between the operatic move and the operation as it forms new ways of acquiring many means of whatever you want to imagine within yourself, and outside of the bound of yourself from the world, or within the world. And so it shows that there are inherent limits to our understanding and predicting the future at all levels of complexity, right? So very hard to predict, right, is what chaos theory... Chaos theory presents a theory of foresight which does not allow for any form of rigidity of model at a long term. And if the rigidity of model is applied, then chaotic variables will be either introduced or will be found to be intrinsically a part of the totality of the process, shaking the deterministic system into revindication of its outcome and its potential to describe the totality of the context, if that is what is trying to be done. But we are in fact talking about the value of certain data points and the significance of certain data points over others. Data points being objectified, measurable representations of reality, which comes and reinforces a certain process and narrative of wealth distribution and wealth accession, as well as interests which are attached to these sources of wealth. It is strikingly beautiful. Shakespeare had it right when he had Hamlet say in Act 1, Scene 5, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Hi, I'm Cordelia Cauliflower. Just look at what chaos has done to me." Where does chaos come from? 3 major developments have made chaos a household word. Breathtaking computing power that enables researchers to perform hundreds of millions of complicated calculations in matters of seconds. The rise in computing power has been accompanied by a growing scientific interest in irregular phenomena, such as random changes in weather, the spread of epidemics, the metabolism of cells, the changing populations of insects and birds, the rise and fall of civilizations, the propagation of impulses along our nerves. Such are all phenomenons which can be described through chaos or chaotic patterning. And so now we are in a zone of chaos theory, which was born when these developments were combined with the emergence of a new style of geometrical mathematics, right? So what this book is proposing is the pictorial or the representational aspects of chaos theory, so that we can come to I think a stronger ontologization of chaos. Beyond the familiar shapes of Euclidean geometry, the non-Euclidean structures of fractal geometry. Right? This idea of the fractalization, which is, it's not even a broccoli, it's a cauliflower, right? These developments have made an impact in almost every field of human endeavor. Chaos theory has been like a sea into which flows the rivers and tributaries of almost every discipline and subject, from mathematics, physics, astronomy, meteorology, biology, chemistry, medicine, to economics and engineering, from the study of fluids and electrical circuits to the study of stock markets and civilization. Defining chaos. Chaos has been variously defined. Here are just a few examples. A kind of order without periodicity, right? So no end or no predictable end. apparently random recurrent behavior in a simple deterministic clockwork-like system. The qualitative study of unstable aperiodic behavior in deterministic nonlinear dynamical systems. And here's another by a mathematician in the field, Ian Stewart. Variable, aperiodic, system, dynamics, nonlinear. The ability of simple models without inbuilt random features to generate highly irregular behavior. Technical definitions of chaos are not easy to understand, so let's begin to familiarize ourselves with its terminology. The language of chaos. Dynamic, change, and variable. Chaos is a dynamic phenomenon. It occurs when something changes. Basically, there are two types of changes. Regular ones studied by classical physics and dynamics, and chaotic ones. There may be other types which we have not discovered yet. What is changeable in a given situation is referred to as a variable, right? Again, very pictorialized, good imagery. Interesting. Systems. Any entity that changes with time is called a system. Systems thus have variables. Here are some examples of systems. The human body, the population of penguins in the Antarctic, molecules in an imaginary box, flu moving through a country, the X-Files, a school. Change is inevitable, except from a vending machine. Defining systems. A deterministic system is one that is predictable, stable, and completely knowable. The classic example of a deterministic system is an old-fashioned grandfather clock. The balls on a snooker table behave within the boundaries of a deterministic system. In classical physics, the universe itself was considered to be a deterministic system. Give me the past and present coordinates of any system, and I will tell you its future. Pierre-Simon Laplace, 1749 to 1827. French mathematician. In linear systems, variables are simply and directly related. Mathematically, a linear relationship can be expressed as a simple equation where the variables involved appear only to the power of 1. Example, x equals 2y plus z. There are no squares, cubes, fourth powers, etc. These types of equations can be solved easily, even if they involve several variables. Non-linear relationships involve powers other than 1. Here is a non-linear equation. A equals 3 times b squared plus 4c cubed. Such an equation are much harder to analyze and frequently need the help of a computer to understand, right? So non-linear functions are the ones which are perceived to be harder to be processed through the computational aspects of the human brain. But that is up to the capacity of the human brain to satisfy the computational aspects of the function. You guys like Pepsi? Periodic and aperiodic equations. A period is an interval of time characterized by the occurrence of a certain condition or event. A variable in a periodic system exactly repeats its past behaviors after the passage of a fixed interval of time. Think of a swinging pendulum. Aperiodic behavior occurs when no variable affecting the state of the system undergoes a completely regular repetition of values. Visualize the flow of water as it goes down a sink. Unstoppable aperiodic behavior is highly complex. And by unstoppable, I mean unstable. Very, very large difference. It never repeats itself and continues to show the effects of any small perturbation to the system. This makes exact predictions impossible and produces a series of measurements that appear random. That's why, in spite of our satellite observations and computer models, it is still impossible to predict the weather accurately. What is unstable aperiodic behavior? So next step, right? So as you understand, you see, I think these pictorial representations are there to further emphasize what it would mean to relinquish order onto the determination of chaos as a symbolic order of representation, right? And so let us continue with what unstable aperiodic behavior means. But you can see that it's far related. It is far related from order, right? Aperiodic meaning no rhythm, tempo, no associated pattern of temporality, and unstable meaning meaning that its reactivity cannot be predicted, right? And so behavior, again, we're talking about the comportement of the system, of the structure. So, okay, what is unstable aperiodic behavior? Behavior that is unstable yet periodic is difficult to imagine. Indeed, it appears to be a contradiction in terms. However, human history provides us with several examples of just such a phenomenon. It is possible to chart broad patterns in the rise and fall of civilizations. We can see that these patterns are periodic, but we know that events never actually repeat themselves exactly. In this realistic sense, history is aperiodic. We can also read in history textbooks that seemingly small, unimportant events have led to long-lasting changes in the course of human affairs. Until quite recently, our principal image of behavior that is so complex as to be unstable and aperiodic was the image of a crowd. Now that our perception has changed, we see such behavior in even the commonest events. Water dripping from a tap, a flag waving in the breeze, the fluctuation of animal population. Linear systems, right? And so once we have ascertained a very complex system which cannot easily be understood through linearity, let us come back to linearity and understand it more fully. So simply put, chaos is the occurrence of aperiodic, apparently random events in a deterministic system. In chaos, there is order, and in order, there lies chaos. The two are more closely connected than we ever thought before. But since deterministic systems are predictable and stable, this seems to be illogical. As a matter of habit, humans have looked for patterns in linear relations in what they see. Linear relations allows us to predict what will happen within a system and can easily be expressed on a graph. In other words, they form a straight line on the graph and we know where that line is going. Linear relationships and equations are solvable. They make them easy to think about and work with. It's just increase in enjoyment and satisfaction, right? Or these are not measures of dimensionality. Nonlinear complication. Nonlinear equations, on the other hand, cannot be solved. Friction, for example, often makes things difficult by introducing nonlinearity. Without friction, the amount of energy required to accelerate an object is expressed in a linear equation. Force equals mass times acceleration. Friction complicates things because the amount of energy changes depending on how fast the object is moving. Nonlinearity, therefore, changes the deterministic rules within a system and makes it difficult to predict what is going to happen. There is a famous example of a nonlinear relationship in the history of chaos. Robert May, a biologist, was studying an imaginary population of fish. The mathematical model he used for the fish population was the equation x to the suffix next equals r times x times bracket 1 minus x bracket. Very simple equation. X to under suffix next equals R times X times bracket 1 minus X, close bracket. This represents the present population of fish in an area, right? The exact amount of fish you can find in one area can be reduced to a parameter, which is R, rate of growth, right? So if you know how fast a population is growing, then you can know in the moment how much fish there are in the parameter. So you found that the rate of growth was 2.7 when the rate of growth was 2.7. You found the population to be 0.6292. Right? What is this result? What is this number that that effectively represents the fish population in an area? As the parameter rose, the final population rose slightly too, making a line that rose as it moved from left to right on the graph. Suddenly, as the parameter passed 3, the line broke in two, and they had to plot for two populations. This split meant that the population was going from a 1-year cycle to a 2-year cycle. As the parameter rose further, the number of points doubled again and again. The behavior was complex, yet regular. Beyond a certain point, the graph became totally chaotic, and the graph was completely blacked in. Yet even in the midst of the chaos, stable cycles returned as the parameter was increased. Right? That's what the graph looks like. Most forces in real life are non-linear. So why have we not discovered this before? The reason that chaotic behavior has not been studied until now is because scientists reduced difficult nonlinear problems to simpler linear ones in order to analyze them. Galileo's work with gravity provides us with a great example. Galileo, 1564 to 1642, an Italian physicist, disregarded small non-linearities in order to get neat results. Feathers do not fall with the same speed as a ball due to air resistance. So what? An ideal scientific world was created where regularities were isolated from actual experience and disorder. Since the advent of modern Western science, we have been living in a world which acts as if the platypus was the only animal in existence. So on that note, I'll continue the lesson in another video where we'll go back to feedback, and this will be one of my many achievements as an educator throughout my life, since it is one of my main profession.